if the velocity and the velocity gradient in that jet, where that jet is dissipating energy, and we know that when it dissipates energy, it ends up causing the fluid to deform, and where that fluid is deforming, if there's a floc in there, and of course there will be, that floc is experiencing this deforming action, which could actually break the floc. And so I was suggesting that if we have too high a velocity gradient coming out of that diffuser, then what would happen? Okay, so we have these green guys coming out, and if the velocity gradient is too great, what will happen to those green flocs? They'll be sheared, they'll become smaller, and then they'll turn into the red guys that are settled too slowly and end up not being caught by the plate settlers. So this is one hypothesized failure mode for this kind of a floc filter system and the Albert design, that if the velocity gradient coming out of the diffusers is too high, it'll cause us a problem. And then the very good question is, well, wait, Monroe, if you're saying that the green flocs can be broken up because the velocity gradient is too high, isn't that jet also right there? The jet is right there in the tank, in the bottom of the tank. The jet is right over here, where it goes around the corner, around the jet reverser, and then it's shooting up right here. And that's where there's lots of energy dissipation. There are blue flocs there too. Won't the blue flocs be broken up? So I went on a trike ride this weekend. It was beautiful on Sunday. And as I was taking my trike ride, I was pondering this question, trying to figure out what is going on here. And so the first thing that you should notice is that Monroe doesn't really know what's going on here either. And so you should be skeptical of everything I'm about to say. Like, you always are skeptical when you're listening to someone, right? But this is what I've done. I've gone back and looked at some of the data that we have from performance of a system where we were slowly increasing the velocity of the jet, and hence the velocity gradient in the jet, and looking at what actually fails. And the signal that we pick up first from failure is too many flocs or particles coming out from the settled water, going right through the plate settlers. That's what we see first. And then later, at even much higher energy dissipation rates or velocity gradients in that jet, we see another failure, or another indication of a problem. We see that the concentration of flocs or particles in the supernatant below the plate settlers and above the floc filter, that concentration starts to go up. So can you tell me what would be happening inside this system that would make the concentration in this region where all the vertical arrows are here, where it's above the floc filter and below the plate settlers, why would that concentration go up? And do you remember what the concentration of particles is in this region? It's the same as something else. Anybody remember? What's the concentration of flocs coming out of the floc filter? Here's the hint. In the pipe coming from the filter are green ones and red ones. And the green ones go right up through the floc filter because they don't settle fast enough, and they just keep on going up to the plate settlers. And they're too big to be picked up inside the blue flocs. And the red ones, there aren't many of them because your flocculator was pretty good. And so there actually aren't many flocs that are too small to be captured by the plate settlers. So that means that the concentration of the green guys, the green flocks coming out of the floc filter is almost the same, or the turbidity that's caused by them is almost the same as the turbidity of the raw water going into your plant, because almost all the particles are in green flocks that are going right up through the floc filter. Okay, so now we have the next mystery. Why would the concentration of flocks increase in that zone when you have a high energy dissipation rate in the jet? A really high energy dissipation rate in the jet. Anybody want to take a guess? We're converting one size particle to another size particle. What are we converting? If we convert green to red, what happens? Not much, because the red ones mostly are, well, okay, some of the red ones are caught in the floc filter, but eventually you would see that as really bad performance, because we would be having more red guys come in. But the blue guys, if we take a blue guy and we break it and turn it into a green one, that will increase the concentration of small flocks that can settle. And so they will be going up through this supernatant. So there is evidence at really high energy dissipation rates that the jet at the bottom of the floc filter breaks up blue flocks and turns them into flocks that get caught by the plate settlers. But the other evidence is that before that even happens, we see failure. We see an increase in settled water turbidity at a lower velocity gradient. And that's because we're turning green ones into red ones. So apparently turning green ones into red ones happens first. So that's the failure mode that we have to watch out for. So those were my reflections. Actually, some of those were my reflections on the trike ride, and then some of them were actually going back and looking at the data and seeing which thing was failing first. So that was just FYI, part of my reflections on the question that I had from one of you last week. And I want to go now to this reflection on learning, because we're having this exchange where I present material and I show animations and I tell stories, and you're trying to figure out what you can learn from what's coming at you. And I'm curious if any of you are willing to share some thoughts you have of what do you do during these presentations that help you actually learn something from it. Anyone willing to share something that you do that you find helpful to help you so you actually learn something?
I find it helpful when somebody asks a question that I might have had or that I didn't have. I like to write it down and then also write down the response, because it's likely that at one point in the future, I will have a similar question. And it'll be nice to have that response waiting for me. And it's also nice I usually have the lecture, the actual slides on my second screen, and I write down notes in that area. So that way, like, I have the main points, but also little points that Monroe might bring up. And I find that that's helpful.
Thanks, Izumi. Others, tricks that you use to remember something by the time you get to the end of lecture?
I always like to try to relate it to like an easier example or like something that makes sense in my head. So I'll be like, oh, the flocculator is like telling instructions to this particle, or like this particle is telling instructions to this, or I kind of like to animate or give them like people qualities when they're not people.
Yes, that's great. So do you have clay particles that are really, really lonely and they wish they could find someone to hang out with?
Yeah, they have little faces on them too.
Nice. Other ideas? Because there are many ways to do this. I'll just then encourage you to think about what you can be doing so that there's something active going on. Because if you can be doing something active while I'm also sharing ideas, it will help those ideas to get in. Even doodling is a fine thing to do. So ponder that one, see what other ideas you can come up with. All right, so now to the beginning of what I was really supposed to talk about today. So there's another failure mode related to plate settlers that is pretty important. And it's called floc rollup, and I'm hoping my animation works right. So this is what we want to have happen. We want a floc to go up and then slide or roll back down the plate. Looks great. And then what happens if we make these plates get closer and closer and keep the same velocity going between these plates? And we get this. Wasn't that so exciting? You weren't expecting that. And because it was animated, it must be true, right? So what happened to the poor second floc that thought it had done a good job? It had nicely settled down and made contact with the lower plate. It should have rolled down the plate, but instead it kept right on going up. Can you see what's happening? Anybody want to comment? What's our failure mode? Oh, and I'm guiding you. I've drawn a velocity profile. The velocity between these plates, it is actually laminar flow between these plates, which means you get this lovely parabolic velocity distribution. So what does it tell you about the velocity close to the plate, but not actually on the plate? The velocity on the plate is, anybody remember? What's the velocity right on the plate? Yeah, good, it's 0, it's a solid 0. But if you're just a little bit away from the plate, what happens with these two different systems? Or more to the point, what's the velocity at the center of the floc in both of these cases?
Dan has an answer, and Dan has an idea in the chat. His microphone isn't working, or is not with him right now. So he says
thank you.
He says that smaller area of flow means it's moving faster, so the poor particle gets pushed along even at the slower outside edges.
Okay, that's almost right. And I may have misunderstood something, but the average velocity is actually the same in these two systems. But the velocity that the floc is experiencing close to the wall is higher in the narrow case, because the velocity gradient has to be steeper, because you still have to have the same parabola squished into that smaller space. The middle of the parabola has to have the same magnitude. So that means that the velocity gradient is steeper. And that means that you go a short distance away from the wall and you hit a higher velocity. And if that, you see what the failure mode is? If the velocity at the center of the floc is higher than the velocity at which the floc would want to slide down that incline based on gravity, then that floc's going to go up instead of down. So I'm not making this up. This is actually a real failure mode in plate settlers. And this is what determines how closely you can space plate settlers and have it work. And I'll explain why you might want to get them really close together in just a little bit. So the connection to sustainability is we can actually make a cheaper plant if we can space these plate settlers closer together. And I'll show you that eventually. So here's the solution scheme. We we find the velocity gradient next to the plate. Based on the fact that it's a parabolic velocity distribution, we find the fluid velocity at the center of the floc based on the diameter of the floc and its radius. And then we find the terminal velocity of the floc down the plate for the case of zero velocity fluid. So this is the floc terminal velocity would have been G times sine alpha. And we set the velocity of the center of the floc equal to the terminal velocity of the floc sliding down. And when those two are equal, that means that the floc will just hang out there and won't go up or down. So that's like right at the failure mode. And we can use that to figure out how closely we can place the plates. So this is a plot showing different plate spacing, minimum plate settler spacing in millimeters. And it's a function of temperature. Temperature ends up being like so important in the design of water treatment plants. And of course you have to design for whatever the critical temperature is. And for sedimentation and flocculation, the critical temperature is the coldest one you're going to have to deal with. So what do I see? So look, you can look at the equation and see some things. For example, S min is proportional to the vertical velocity between the plates. That means that if you have a higher upflow velocity entering the plates, you have to use a larger spacing. So Agua Clara uses a lower upflow velocity than some of the conventional designs. And that means that we should be able to get away with a closer spacing of the plates as well. Another thing to point out is that a really important factor is this density of water divided by the density of the core particle that makes up the floc. Like it could be a clay particle or it could be some dissolved organic material that is become particulate, minus the density of water. So for flocs where the core particle is not very dense, that density of core particle minus density of water can actually approach 0. Those two densities can get very close together. And if those densities get very close together, the equation blows up. And it says you're going to need really widely spaced plates so that you don't have this problem. And that is kind of one of the big areas of unknown for us. We know that if you have flocs that are made primarily out of dissolved organic matter, that they are super challenging to capture. And that's the reason that the density of the core particle is very close to the density of water. And so they will happily just slide up the plates, even if you do get them to land on the plates. So if the density of the core particle is at least 1,150 kilograms per meter cubed, the red line, then it looks like we could get away with 20 centimeter plate spacing and we'd be fine even for the coldest temperatures. The problem is that we don't actually know like what the density of the core particle is that is our critical case. And this is where there needs to be more work to characterize what the core particle density is that you're trying to remove as a function of the raw water quality. More work to be done. So anyway, we use 2.5 centimeter spacing. That's the plant that I have here in the middle of the slide. Spacing has a big influence on how deep the sedimentation tank has to be, so that the tank gets deeper as the plate settler spacing increases. And do you see why that's true? If I increase the plate settler spacing, in the plate settler equation, the length of the plate settler divided by the spacing is an important dimensionless parameter. So if I increase S, I have to also increase L to get the same thing out of it. So you can see that in the drawings, as you go from 1 centimeter spacing to 2.5 to 5 centimeter spacing, the plate settlers get longer and longer, the other thing that's happening is in each of these designs, the total area of plate settlers is actually very close to the same. So in order to get all that area in there, we have to have longer plates when they're further apart. And so conventional designs, conventional plate settlers use 5 centimeter spacing. We've dropped that to 2.5 to make a more compact plant, but we're not going to go to 1 centimeter because the analysis suggests that we would run into failure if we went to 1 centimeter, although it would be a cute little design, but it wouldn't work. Cute, but okay. Okay, that's my conclusions. We're trying to catch flocs that have sedimentation velocities greater than the settle capture velocity. And that is about plate area, the plan view area. And then the spacing determines whether flocs are going to keep on rolling up or whether they're going to do what we want, which is slide back down and turn into blue flocs. So some confusion. We don't yet have a basis for choosing a settle capture velocity based on overall plant performance. Our settle capture velocity is something that we pulled out of the air. We pulled it from a website, but it wasn't based on first principles or physics. Same thing I would say for our spacing. We knew that convention was 5 and we decided we were going to go less, and we went to 2.5, but that was also a number pulled out of the air. It's possible that 2 would be fine. It's possible that 3 would work better. Things that we don't know for sure. Okay, so now I want to present this idea of things that can go wrong. So here's a thing that we ran into early on, where we had this thing that we called floc volcanoes. So these were, like, you look at the sedimentation tank and you'd see places where there were flocs just coming up, right up through the plate settlers and all the way to the top of the water in the tank. They would be intermittent, and it happened at the plant that was built for San Nicolas. And what was sad is the raw water turbidity was only 4 NTU, which is, you can see that in a glass, but it's not very dirty. And then the settled water turbidity, after it went through our floc filter and plate settlers, it varied between 0.5 and 4 NTU. So the 0.5 was decent, but the 4 NTU was like, goodness, we're not doing a thing. So this is the question, like, why is this happening? And in order to lead you along this story, here is some data from the plant. So they're measuring the settled water turbidity is the red lines, and the raw water turbidity is the blue lines. And the raw water turbidity has some little spikes in it. I don't know if it rained a little bit or what happened, but there was little spikes in turbidity. But really, these are all very low turbidities. It should be easy to treat this water. But look at the settled water turbidity, and I'll guide your eyes. Look at this. There's a peak. There's a peak. There's a peak in there. Okay, I missed one in the middle there, but the one in the middle, I'm not sure what that one's from, but it's likely from the peaks that were happening in the raw water turbidity. There's another peak. There's another peak. So what do you see? When are these peaks happening? Don't be shy. Tell me, what do you see in this graph? What do you notice about any trends or something that's curious? Okay, I'm going to ask Katie. Katie, what do you think?
The peaks are happening like in the middle of the day.
They're happening in the middle of the day, and that's great. And so why do you think, what might be going on? Any other clues? Like what could this be connected to if it's happening in the middle of the day? Like, did they get hungry?
Could it be
That
like
was
temperature?
brilliant. So Katie, you're exactly right. It's about temperature. And what's the effect of temperature on water? Because it does two things to water. Let's go down. There's two water properties. It changes its viscosity. Which way does that go? If it gets warmer, what does viscosity do?
Viscosity decreases.
Viscosity decreases. And when the viscosity decreases, that ought to help us. Because in the flocculator, that means that the fluid deforms more easily. And so there should be more collisions. And in the sedimentation tank, the terminal velocity of the flocks will be higher because it's less viscous. And so we should be able to remove them easier. So viscosity was a dud as far as explaining this. What about density? What happens to density when the water warms up?
Same trend also decreases.
You're right. It also decreases. I had to think about that for a little bit. So the water temperature increases, the density decreases, unless you're right at 4 degrees Celsius, and then there's funkiness, right? But we were warmer than that. We were in Honduras. So anybody see what might be happening? Should I tell the story? Okay. The story is, see, you didn't know all the information, but the story is that this community has a 14-kilometer transmission line. That's the pipeline that's bringing water from, it's actually a cave up high in the mountains where the water comes from. Oh, and this is a funny story. Every once in a while, the water coming out of this cave gets really turbid, which is why they need a water treatment plant. And it's a bit of a mystery why water coming out of a cave gets really turbid, because you'd think this is groundwater, right? So the local folklore is that there's a snake in the cave, and the snake gets very active at some seasons of the year, and that's why the water gets turbid. I don't actually know what's going on there, except, do you know about what karst means? The fact that there's a cave is consistent with the idea that this is a karst region. Karst means a limestone region. And in a limestone region, water can be dissolving the limestone, and so you end up having caves. And that means you can have water flowing underground in rivers, in channels. And so water that is subsurface in a karst region is not necessarily being filtered in the way that you normally think of groundwater being filtered. You can have completely dirty water flowing in underground rivers. And indeed, I've been at a river in Honduras where it's a nice sized river and it flows right up to a mountain and goes in. That was, and as we walk back to that region, we get to see caves as well and go into caves. So it all fits, right? There are caves, and the river can actually just dive into the mountain. And maybe it's that same river that's showing up on the other side of the mountain coming out from this cave with turbidity in it. Okay, so that was all along, that was a free story that had nothing to do with this problem, except that we've got dirty water. It comes 14 kilometers, and a lot of the terrain that they're bringing this pipeline on is pretty rough. And so they weren't able to bury the pipe. So they used galvanized iron pipe, and it's just laying on the surface. So it's exposed. And another piece is that the water board that runs this system was very conscientious, and they wanted to do a good job of maintaining their system. And so they kept that trajectory of that pipeline cleared. So they would send people up there with machetes and they would keep it cleaned. So that means that there's sun shining on their pipeline for 14 kilometers. And so you have a solar water heater. And so I don't have that data, but indeed the temperature was going up nicely every day, significantly. And that meant that the water at noon, the water coming into the plant is warmer than the water that is in the plant. So you have a tank of water, like in the sedimentation tank, you have a tank of water and it's kind of cool, and you have warm water coming in the bottom. Now, do you see what happens? You got warm, buoyant water, and it just races to the top. And it goes to the top so quickly that there's not a chance for the flocks that it's carrying to either get caught up in the floc filter or settle out in the plate settlers. So that was an interesting insight. And the problem is, we don't know how to solve this one. It's a problem. It's a problem with water treatment plants everywhere. We did advise that they stop cutting back the weeds next to the pipeline so that the pipeline would at least have shade, but that doesn't completely solve the problem because it's the environment is still warmer, and so the pipeline still warms up. And yeah, an ongoing problem that doesn't have a great solution. And here's something that I'm working on currently related to sed tank design. I think that the water exiting our diffusers in the bottom of our tank may be breaking up flocks under some conditions. And so I'm thinking we need to slow those diffusers down. And so I'm working on a design that would allow us to do that. And the design challenge that I've created for you for after you're done with the flocculator is going to be exploring a little bit of like the cost trade-off of what happens when you try to slow the water down in those diffusers. So now, some play. We're going to compare some designs. So first one, this is a CEPIS plant. This is designed by the Pan American Health Organization. This is water from multiple sources coming into a plant. And right along here somewhere, they're going to be adding coagulant. There's a little hydraulic jump or a little waterfall. And then right there, they're adding the coagulant. The water continues on and goes into the plant. And there's my Cornell students hanging out. And on the right are flocculators. So these are flocculators that the water goes back and forth around these wooden baffles. And on the other side are sedimentation tanks. So you can see the effluent manifolds, and you can see plate settlers down in there, and you can see some students, and that was the end of that. So what I'd like you to do is stare at this design. So this is, I'm sorry, the image is as good as I was able to get. This is an image of what's happening inside their version of a sedimentation tank. And I want you to like take what you've learned so far and think about what might go wrong. And I realize I didn't set up well for doing this. So maybe we'll stay here, but I really want you to like be brave, type things into chat if you don't want to say it out loud. And I want you to think about what might go wrong in this design, or how might you make it better? And if you can read Spanish, all the better, right? Because this was all put together in Spanish because it's out of a manual produced in Peru. I want to like show you how a water particle goes through. I can kind of do this animation. So it begins in this canal distribuidor de agua floculada. So this flocculated water channel. That's right in the middle of the page where my blue dot is. And that blue dot is going to go down through an orifice and into the bottom of the sedimentation tank, find its way over, flow up in between the plate settlers, and then into this outlet channel, and it's gone. Okay, so that's roughly the path of water. Sorry, you can't follow that because you can't see when it's behind things and when it's going, between plates. But that's the path. Now, critique the design. What do you think might not work well in this design? Or if you were a plant operator and had to do some maintenance on this plant, what would you find awkward? Man, I want to encourage each of you to type something into the chat, okay? Don't be shy, type something into the chat. Oh, there's a great question. Are those plate settlers made of asbestos cement? And that is exactly what they say. They are made of asbestos cement. And I'm betting you're thinking that's not a good idea. And you are right, it's not a good idea. I think this design was made before, well, I just was looking at their manual this morning, and they have a picture of plastic plate settlers that failed because they got brittle, which goes to another insight that Agua Clara has had, and that is that all water treatment plants should be under roof to protect the system from sunshine. This is a revolutionary idea in the world of water treatment, that you should have a roof over a water treatment plant. And that actually makes it so that plastic plate settlers work and are a solid option. What don't you like about this one? Don't be shy, type away. I want to see lots of chats. One of the ways to think about critiquing is, if something went wrong, and you can think about all the possible things that might go wrong, how would you fix it? So there's a flat bottom to the tank. So what do you think? What's the issue with the flat bottom? Anyone?
Would it cause a lot of those particles to build up at the bottom, and they have to go inside there and wash it out? But the sedimentation plates would also make it hard to get in there and clean all that stuff out.
Yeah, lots of good comments there. Yeah, so sorry, I missed your comment, Eric, earlier. Yeah, so there would be sludge accumulating on that flat bottom. You now know that if there's a flat surface, sludge is going to accumulate on it. Okay, so how does the sludge get out of the bottom? Do you see that? I didn't detail that, but there's these little holes. Like, here's a little hole, and that little hole is connected to this drain channel. So there's a valve at the end of that drain channel. Presumably they open up that valve and it starts sucking out of those ports. What do you think about the ability of those ports to empty the sludge that's sitting on the bottom of the sed tank? So one possibility is that hole could clog up pretty fast. Yeah, and they're elevated off the bottom, so they wouldn't even get all the sludge. And I have to explain another thing about fluids. Have you all used a vacuum cleaner that has the option for connecting the hose to the blower end so that it's discharging a jet of air? And have you noticed that you can use that and you can blow dirt away from a pretty long distance? Now, connect it the way it's supposed to be, with the vacuum cleaner sucking through that tube. And arguably, it's the same velocity of water going through the tube in both cases because mass is conserved, right? What's going into the vacuum cleaner has to come out. But how far away can you suck into a vacuum hose? Like it's I don't know, something like, is it something like maybe 10 centimeters? Whereas you could probably blow it away, maybe even more than a meter. Depends on how strong your vacuum was. Right? I'm not making this up. This is real. And it's the same velocity. So what's the difference? This is like, there's some good pondering happening. What is the difference? Okay, so when the discharge is coming out of the vacuum hose, that's got momentum. It's a jet, and it just keeps on going kind of in a straight line, and it slowly entrains fluid from around it because it's turbulent, and that jet slowly expands, but it travels forward really far as it's slowly dissipating into the environment. The reverse, when you have a vacuum sucking, now the fluid that's entering that hole comes from everywhere. It sees this as a sink, and it comes from all around the vacuum, even from back behind the vacuum. It comes around and it goes into that hole from everywhere. So it's pulling air in from like a sphere. Air is flowing in spherically, like, I'm not using the right words, but it's all coming in like a sphere towards that center point. And that means that the velocity, as soon as you get just the tiniest distance away from the vacuum hose port, the velocity has dropped off tremendously. And here's the fun part. Humans, we breathe through our noses. When we exhale as a jet, and it travels a nice long distance. When we inhale, we bring air in from close to us. If that weren't the case, if it were the same in both directions, we would just be exhaling air and breathing the same air back in again. But when we exhale, it's a jet. When we bring it in like a sphere coming in. So anyway, to this point, now you know that those drain holes for the sludge are not going to be sucking sludge in from across the bottom. So it will not clean. I'm going to go back to looking at your comments. So the question about the launders, it seems like the launders are spaced, the launders or the effluent manifolds, you can see two of them there. I'm not sure if this drawing is completely correct according to their design, although it might be. We can look at a picture in a second. And yes, you do need to keep the distance between those effluent manifolds not too far apart. Otherwise, you won't be using all of your plate settlers well. The left side is open because we are doing like a cut. We did a section cut for this drawing. It's not actually open. So that was great. Here's another thing that I think would be a problem, and that is, how do you get underneath these plate settlers to clean out the sludge that we now know is going to accumulate there? Because you're not going to be lifting out all those asbestos plates. By the way, asbestos plates are a bad idea. They aren't as bad as you might first think, because drinking a little bit of asbestos is not actually that hazardous. It's inhaling it that's the problem. However, when you're taking your shower, you're inhaling air that is very moist from the water, and so that's where the asbestos connection would be. Don't worry, we're not using asbestos plate settlers in our designs, and I'm sure they're not either. This is an old design because they were very active decades ago and are no longer so active. Okay, so that was great. Critique the design. You got that one. And I would also say that there's a fair risk that sludge would accumulate inside that channel. I'll show you more about that in a second. And I'm curious how they're suspending their plate settlers. And I'm also curious, like, how do you assemble this channel system where there's the collection channel on top of the inlet channel, and that looks like a rectangular box. It's too small for a person to get in there. So I'm not it's not clear to me how you actually fabricate that. So here's a view of that same design, but now from a nice photo. And you're seeing the spaced out launders or effluent manifolds. They're not very far apart. So they seem like they're closer in this actual photo than what they were in the drawing. This concrete slab that we see on the left of the photo is where those channels are buried. So the inlet and outlet channels are buried underneath there. And there's a cover that would allow you to see, I guess, the effluent or exit water. There's a subtle thing here. See where the water level is relative to the orifices on these pipes? The water level is right at the orifices, which means that the level of the orifice is actually determining the level of the water in the tank. And that means that if those those effluent manifolds are not perfectly level, if they're sloped a little bit, then the orifices are sloped, and then it will preferentially pick up water from the lower orifices. You see that? If the orifices are sloped, if that pipe isn't level but it's sloped, then the orifices that are down further will be the ones that will get all the water. Right? There's holes all along here. The lower level orifices will have a higher head pushing water in, so they'll get all the water, and you won't get uniform flow. So we get around that problem of having to have precisely installed manifolds by having the entire manifold submerged, and then the pipe is full of water. Our manifold or our launder is actually full of water as well, and so it doesn't matter if it's sloped or not. Okay, and I want to go for like another 10 minutes, and then we'll go to gather. I want to talk a little bit about the agua clara evolution, and we'll at least start on this. So I wanted to be clear that we also made some very bad designs. And I would argue that we continue to make mistakes, and we continue to learn from those mistakes. So here's our very first plant, Ohohona, and it's basically a rectangular box. We designed the simplest thing possible. It's a rectangular box, and now you know there's going to be sludge accumulating in the bottom, and it's going to be a pain. Then we went to another design, and I realized the image is not great, but we now have a sloped bottom, and we have, in this case, there are 4 pipes that are bringing water in. So each pipe goes in and then ducts down and is blowing water towards the bottom of the tank. And there's 4 of them coming in at different places. That was at least a slightly improved design. So there you can see more clearly 3 inlets dumping water into the bottom of the tank. And then I'll show this one. So this was our next improvement after those previous ones. And we're in this search of, we're trying to get a floc filter in the bottom of our tank. And so we have this idea that we're going to have water that at the end of this photo, at the top is the inlet channel, just on the other side of that concrete wall. And so our water particle is in that inlet channel, and it's going to drop straight down from that channel through what's like a vertical chimney. It's a rectangular opening that the water can flow down through, and then it will pop out underneath this sloped bottom. So this is where the water travels. It goes down, and then it goes down the chimney, then it pops out of a hole underneath those slope pieces. It comes up through the port that was at the very bottom of the sedimentation tank that these slope pieces create. And it looked just like, this is a wonderful design. But maybe you're already thinking you see some problems with this based on what we've been learning. So let's look at what actually happened. So now I'm showing you the good and the bad. on the left is what it looked like when we made it, and on the right was a few months later. And you can see there's a worker in there with his boot. I'm showing half the image. And look, we had envisioned our flocks flowing into the middle of this sedimentation tank and settling out there. But the flocks didn't get the message. And so they thought, well, why not hang out in this triangular region back here? And they settled out there instead. And they thought that was perfectly fine. But look at this. I don't know if you can tell, like here, there's this nice brown dirt, but look here. Do you see that there's some other color showing up here? It actually is black. And it's because it's anaerobic. And the workers said it really stank when they cleaned this out. And it was a pain to clean out. So I hope that you are now being indoctrinated in this idea that sedimentation tanks need to be cleaned, need to have a design that keeps them clean all of the time. And for agua clara, where we're not using scrapers to clean them, it means thou shalt have no flat surfaces. Because everywhere where there's a flat surface, flocks are going to accumulate, you're going to get sludge, and it's going to be a mess. And with that, I will break, and we can go to gather, and I'll come around and see how each of your teams is doing. But before we split, anybody want to ask a question here? A question you have about what I just showed you, about why flat is bad. Okay, then I'll see you in gather in just a minute. Be well.